Okay, now I'm going to talk about eigenvalues, and we're going to talk about eigenvalues because they're very important descriptions of state space models, and we'll see that actually the eigenvalues of the A matrix in the state space equation x dot equals ax plus bu relates to the stability and lots of properties of the system. What is the eigenvalue problem? Well, the eigenvalue problem can be stated simply by the matrix equation ax equals lambda x, where A is a matrix, a transformation matrix, x is a vector, lambda is a scaling factor. And all this equation is saying is that if we have a vector x, which is going to be a column vector, and we multiply it by transformation A, all this transformation does is scale the magnitude of the vector. Typically A is going to be an n by n matrix, so we'll be dealing a lot with second order systems, so that'll be a 2 by 2 in our case. X has got to be a corresponding n by 1, so that if it was a 2 by 2 system, we'd have 2 states in the x vector. Lambda is just simply a scaling constant. And we need to solve this equation in order to find the eigenvectors, which is going to be the x that solves this, and also the lambda which solves it. In fact, we care more about the lambda because that's the eigenvalue of the system, and that's what we care about particularly today for this course. So what does that look like depicted graphically? So in this particular example, what we're doing is we're starting off, when it's all square, we're starting off with vectors which are blue, pink and red, and then we multiply it by a vector A, which is becoming increasingly strong in terms of stretch, from doing nothing to doing quite a bit, from doubling it or so. And what we see, there are certain aspects of the vectors that we can see on this drawing. First of all, the blue vector, when we put in the big transformation, we see it stretches out, but it still points in the same direction. So we'd say that that was an eigenvector because it's keeping its direction under the transformation, but it's not changing the it's changing the magnitude, right? But it's not changing direction. The pink ones also are keeping their direction, right? So they're also eigenvectors. But if you look at the red ones are actually changing direction, so they would not be eigenvectors. So how can we actually find them? So let's think about a concrete example in terms of, let's say, a 2 by 2 system. We're going to consider this A matrix as being an A matrix off a state space model, so x dot equals ax plus bu. This could be a typical A matrix, which is the state transition matrix, if you like. Let's now find its eigenvalues. We're not going to look at the eigenvectors in this course, so let's not bother. So in order to find that, we've got to solve the equation ax equals lambda x. And we can rearrange this equation. First of all, we can put everything equal to 0, so x minus lambda x equals 0, and then we're going to factorise the x out. In order to do that, we can't just have the lambda on its own, because it's basically, this is a matrix equation, so a scalar on its own is not a possibility, so we have to multiply it by the identity matrix before we take it away. So A minus lambda I times x, where I is the identity matrix. Now there's a trivial solution to this. If we could find the inverse of A minus lambda I, what we could do is we could multiply both sides by that, and that would then basically get rid of the A minus lambda I component. We'd end up with the equation x equals 0, and that's not a very good solution because that's a trivial solution. What we actually want is when the determinant A minus lambda I is 0, so there's not a trivial solution to this. So that's what we're going to look for. We're going to look for that condition, and in order to do that, we need to find the determinant A minus lambda I. So determinant is written in lots of different ways. I prefer the way written with det, but you can also see it quite often written with the matrix equation in between a couple of vertical lines. So let's evaluate this expression, determinant A minus lambda I. So we're just expanding it out. Here's the A minus lambda times the identity matrix. And then we do an element for element subtraction. So 1 minus lambda times 1 minus lambda here. 0 stays as 0, 1 stays as 1, and then it's 2 minus lambda times 1 here. And then you'll hopefully remember the determinant of a 2 by 2 matrix, if its elements are A, B, C, D, is going to be AD minus BC. So it's 1 minus lambda times 2 minus lambda, take away 1 times 0. So we've just got the 1 minus lambda, 2 minus lambda. Now by inspection we see that this is, has a solution when either of these terms in brackets goes to 0, and that's quite easy to find. So when lambda is 1, the first bit goes to 0, and when lambda is 2, the second bit goes to 0. So the solutions then are lambda equals 1, lambda equals 2. Okay, so that's a little bit on how we calculate eigenvalues. Now let's look at why we actually care about that, and we're going to do that by looking at the transfer function of a state space model. So we've already looked at state space models a little bit, and we've looked at how to calculate transfer functions. It's the output divided by the input. Let's do that for a state space model. And we have two equations, x dot equals ax plus bu, and y equals cx plus du. And so the input's going to be u, and the output's going to be y. That's what we care about. And we've got to get rid of everything else. So let's take Laplace transforms like we would normally. And of course x dot, right, just because it's a vector, it doesn't matter. X dot in the S domain goes to S, x of S, and everything else just goes from what it was just to its Laplace variable version. Collecting up terms, again using the trick with determinants, factorising out x of S, so we end up with Si minus A times x of S equals Bu of S. And we can multiply both sides by the inverse of Si minus A in order to get x of S on the left hand side, right? So we can do that. Now we have our output equation, and we take the Laplace transform of that, and we end up with y of S equals C, x of S plus du of S. And now what we're going to do is we're going to substitute in the x of S that we've just had before into here, so we can get rid of the x of S term. Right, so that's what we've got here. All of this lot here goes in there, so we've got C multiplied by all of this lot plus du of S. Now we're going to collect together all the u of S terms, because we need to calculate this this ratio in order to get a transfer function. Now we've got y of S, which is the output, in terms of this scaling factor in front of the input. And what we care about is output divided by input, so we divide basically both sides now by u of S, and we end up with the transfer function, which we get as C Si minus A inverse times B plus D. So if we start expanding the inverse matrix term, we are aware that the inverse of a matrix is given by the adjunct of the matrix, that's the fiddling around and moving around of elements, divided by the determinant. Right, so now what we see basically is, when is this thing going to have poles? So well, we know poles happen when the expression goes to infinity. When will it go to infinity? It'll go to the infinity when the denominator term here goes to 0, and the denominator thing here will go to 0 when this term with the determinant goes to 0. So when the determinant of Si minus A equals 0, we get a pole. So therefore we see the poles of the transfer function correspond to the eigenvalues of the matrix Si minus A. And that's the relationship between eigenvalues and poles in a system. So for the system x dot equals ax plus bu, we can look at the stability of the system by calculating the eigenvalues lambda of the system matrix A, which is solved by finding the determinant of A minus lambda, well, by solving the determinant equation, A minus lambda I equals 0. And the consequence of this is then, we can then say, yes, now we can say a lot about the system. And just like poles, if eigenvalues have a negative real part, the system will be stable. If they have a positive real part, the system will be unstable. If the real part is 0 and they're actually lined up on the imaginary axis, it's neither stable or unstable, it's going to be marginally stable. And if we've got a complex part in there as well, there's going to be oscillations. So it's just exactly the same as we thought before when we were considering poles, which is a nice result.